Before we look at the bandpass filter, we first need to look at the operational amplifier, or op-amp. In a circuit, the op-amp has a symbol that looks like this. It has 5 pins: the non-inverting input, the inverting input, the output, as well as the positive power supply and the negative power. Here's the equation of the voltage output of the op-amp. Here, AOL is the open loop gain of the amplifier. Open loop meaning there is no feedback going from V out to any of the V plus or V minus. All real op-amps have a much more complicated circuit within them, full of transistors, resistors, and capacitors. But we don't need to worry about any of that for our case. We will assume that we are using the ideal op-amp, and this is the assumptions we make. The ideal op-amp will have an infinite open loop gain. AOL, in our case, from the previous equation, will be extremely high. The op-amp will have an infinite input impedance. This means the current going through the V plus and V minus pins will be 0. There will be 0 input offset voltage. This means the voltage at the non-inverting input and the inverting input of the op-amp will be the same. Essentially, the 2 pins will be at same potential and there will be no current going through them. The ideal op-amp will also have an infinite output impedance, and there won't be any noise from the operation of the amplifier.
Here is an inverting amplifier where gain from V out to V in is V out over V in. Let's replace the resistor component in the circuit with impedances Z1 and Z2. Now we can analyze the gain as Z2 over Z1. To use this type of circuit as a bandpass filter, a designer will need to pick impedances that respond differently to some frequencies than others. For example, a designer picks a Z1 that approaches infinite impedance as omega approaches 0 will result in a gain of Z2 over infinity at low frequencies, and another option to the designer is to manipulate Z2. If Z2 is selected such that Z2 approaches 0 impedance when omega approaches infinity, the gain will be 0 over Z1 at high frequencies and Z2 over Z1 at lower frequencies. The resulting circuit is what is known as a low-pass filter because high frequencies have 0 gain. To select a specific band of frequencies, the designer may choose Z1 and Z2 values such that at high frequencies the signal is dropped due to the Z2 component, and at low frequencies are dropped due to the Z1 component. The resulting circuit is known as a bandpass filter. Here's a set of values that we will use to represent Z1 and Z2, applying the properties we just discussed. Gain is computed in decibels, frequency is used for the x-axis, and gain will be on the y-axis. The resulting graph confirms our theoretical discussion. The low-pass filter shrinks the signal Vi when the frequency is high, and the high-pass filter shrinks Vi when the frequency is low. The bandpass filter has both properties and only allows for a narrow band of frequencies to pass.
Here we have an example of a inverting bandpass filter which consists of one op-amp, 2 capacitors, and 2 resistors. We can analyze the transfer function of this circuit as V out over V in, which is going to equal negative Z2 over Z1, where Z2 is the impedance of resistor 2 and capacitor 2 in parallel, and Z1 is the impedance of capacitor 1 and resistor 1 in series. Solving for Z1 and Z2, we find these expressions, which you should note are dependent upon omega, the frequency of input voltage. And solving for Z1 and Z2, we find these expressions, which you should note are dependent upon omega, the frequency of input voltage, and that's because of the capacitors in the circuit. So as we know, as frequency approaches infinity, the impedance of a capacitor goes to 0, in other words, a short circuit, and as frequency goes to 0, the impedance of a capacitor goes to infinity, or otherwise a open circuit. So using these equations for Z1 and Z2, we can do a quick analysis for how the circuit is going to behave at very high frequencies and very low frequencies. So if we let omega equal to infinity, find Z1 is equal to R1, and we find Z2 is equal to 0, and therefore the transfer function of the circuit VO over VI is going to equal to 0. Similarly, at omega equals 0, we find Z1 is equal to infinity and Z2 is equal to R2, and therefore VO over VI is also equal to 0. So from this, we can essentially deduce that for very high frequencies and very low frequencies, all content in that range is being filtered out, which we would expect that's characteristic of a bandpass filter. So plugging the equations for Z1 and Z2 into the transfer function, we find this expression, and this expression will generate a plot that looks something like this.